Module 2 addresses each of the package support systems: air, start, fuel, governor, oil, and electrical systems. When you've completed this module, you should know the functions of each of the support systems, the function and operation of the system's components, and the operational sequence of events of each system during a package start.
In previous lessons, you learned how air is used to create power as it passes through the turbine. In this lesson, we will discuss the small portion of compressed air that does not enter the combustor, but is bled off the compressor and diffuser sections for use in pressurizing oil seals, cooling turbine rotor discs and first stage turbine nozzles, assisting in obtaining smooth engine operation by preventing surge, and in providing an air pressure signal to control fuel flow. In order to prevent leakage of lube oil from the engine bearings, a carbon-type seal is installed at each of the 4 engine bearing locations. The number 1 compressor forward oil seal is pressurized with air from the compressor 5th stage. 8th stage compressor air pressurizes the number 2 and 3 oil seals located here at the aft compressor rotor and here at the forward end of the turbine section. Compressor discharge air, PCD, is tapped off the combustor housing and is routed through an external air line to pressurize the number 4 turbine rotor aft oil seal and the turbine bearing housing. On some packages, an external line routes air to pressurize the output shaft seal. Oil seal airflow is exhausted through the oil tank vent. Back pressure could result if improperly sized vent lines are used. A test of back pressure should indicate no more than 1-inch water gauge. In addition to pressurizing the number 2 and 3 oil seals, 8th stage compressor air is used to cool the turbine rotor disc. You will remember that during low speeds, an increasing pressure builds up in the engine compressor, which can stop the flow of air. A bleed air valve mounted on the compressor case bleeds this excess air from the 6th stage to prevent surge and to assure a smooth acceleration and deceleration. The valve is a normally opened, power piston actuated, spring-loaded valve. The piston valve operates to close a series of ports in the bleed valve housing. PCD air from the forward end of the combustion chamber is connected directly to the power piston cylinder. When the engine start cycle begins, the piston spring holds the valve open. As engine speed increases, compressor discharge pressure at approximately 33 psig begins to move the power piston, overcoming spring pressure and closing the valve. The valve is fully closed when compressor discharge pressure has attained approximately 48 to 54 psig and the engine has attained approximately 90% speed. These values will be different depending on altitude, so check your operation and maintenance instruction manual. The final function of air is to assist in the regulation of fuel flow. Compressor discharge air provides a pressure signal to the fuel control valve. This signal is used to assist in regulating fuel flow for the proper fuel-air ratio in the combustor. The control air line provides pressure to the fuel control valve and to the PCD gauge located on the forward panel. A more detailed description of this PCD function will be described in the gas fuel systems lesson. This concludes the air system lesson. Read your student guide and answer the questions in the student activity before going on to the next topic.
In this lesson, we'll discuss how the pneumatic start system functions to supply the rotational energy necessary to start the turbine engine. More specifically, we'll discuss the operation of the individual components as well as how they work together in their proper sequence. The components in the pneumatic start system can use either pressurized air or natural gas as the powering force. Since most pneumatic start systems use natural gas to rotate the starter, we'll use the term gas throughout this lesson. For a moment, let's take a brief look at the components that make up the pneumatic start system. As the gas enters the package, it first encounters the starter motor shutoff valve. This valve simply functions to turn the gas supply off or on. With the valve in the on or open position, the gas will travel through the lubricator to pick up a fine oil mist and then enter the pneumatic starter motor to begin rotation. The buffer oil valve mounted here is used to prevent starter motor gas from entering the accessory drive area. Now that you're familiar with the basic function of the overall system, let's discuss how each individual component operates. Once again, we'll follow the gas flow as it enters the package. The optional Y-shaped strainer is the first component in the flow path. It's mounted just forward of the accessory drive area on the outside of the skid base frame. It consists of a cast steel exterior casing containing a 40 mesh screen. This screen is designed to strain out the larger particles of debris that may be found in the supply gas. In the lower branch of the Y, there is a convenient cleanout plug for servicing the strainer screen. The starter motor shutoff valve, mounted just above the strainer, inside the package base frame, controls the main supply gas to the starter motor. The starter motor shutoff valve is a spring return, normally closed, two-way spool valve. The valve is actuated by a pilot solenoid mounted directly on the shutoff valve casing. In this condition, pilot gas, tapped off the main inlet supply, is internally filtered and trapped by the de-energized solenoid core. The main spool is held in the closed position by a spring, while the other end of the spool is allowed to vent through the pilot solenoid valve. When the solenoid is actuated, the core is magnetically raised and allows the pilot pressure to shuttle the main spool valve by overcoming the spring tension and venting that area. This spool position now allows the main supply gas to pass on to the lubricator. An inline lubricator supplies atomized oil to the starter motor vanes. The lubricator includes an adjustable flow valve, a 2-quart capacity tank, and a sight gauge. Looking at this cross-sectional view, we see the lubricator's internal operation. As the main supply gas enters the unit, a portion flows downward, pressurizing the oil in the bowl. This pressurization forces oil up the center tube to be delivered to the main gas flow. The delivery rate is set to 60 drops per minute by an adjustment knob at the top. The next component in the flow path is the starter motor itself. After the gas passes through the lubricator, it enters the starter motor through this port and causes the starter to rotate. Inside the starter motor is the rotor assembly. The rotor assembly contains vanes that move freely in and out of the rotor. Also inside is a cylinder sleeve with an off-center internal bore. The off-center bore allows this crescent-shaped area where the incoming gas pushes against the extended vanes to begin rotation. The pressurized gas enters the housing and passes through these 3 inlet ports to the inside cylinder sleeve. Once inside the sleeve, the gas pushes on one or more of the extended vanes to cause rotation. Since this motor requires continuous gas flow, it's important to keep the exhaust vent free from any obstruction. The starter shaft is connected to the splined interconnect drive shaft with a sprag clutch. The clutch functions to transfer rotational motion from the starter shaft to the accessory drive shaft, thus creating the initial rotation of the engine. The clutch incorporates wedges called pawls. When the inner race, which is connected to the starter shaft, begins to turn, the pawls will stand up and wedge themselves between the spaces of the inner and outer races. When the engine reaches 60% speed, the start system will be de-energized. The pawls will then lie down and disengage the starter motor. Before leaving the starter motor assembly, you should be aware that lube oil is supplied through this fitting and that the clutch assembly uses buffer oil in conjunction with a gas seal to prevent starting gas from contaminating the lube oil in the accessory drive area. The buffer oil is regulated by the buffer oil valve located next to the starter motor. This particular valve is a spring return two-way spool valve, but in this instance it is pilot gas operated. Pilot gas tapped from the main line to the starter motor enters the valve here. This pressurized pilot gas overcomes the spring tension and shuttles the spool valve down to allow oil to pass to the buffering zone. Now that we're familiar with how each component functions, let's see how they work together as a system to start the turbine package. Supply gas to the start system should be clean and dry and approximately 850 standard cubic feet per minute at 140 to 150 pounds of pressure. As the gas enters the start system, the first component it will encounter is this optional strainer with a 40 mesh screen. This is to separate out scale or rust that may have gotten into the line upstream of the start system. Once the gas passes through the 40 mesh strainer, it will next encounter the starter motor shutoff valve. This is a normally closed solenoid operated valve that opens when signaled by the control system. Once the shutoff valve has opened, the gas will flow on to the lubricator. The 2-quart lubricator supplies 60 drops per minute of oil to the starter motor. This 60 drops of oil is going to supply the starter vanes with sufficient lubrication to prevent undue friction or even sticking of the starter during operation. Flowing out of the lubricator, the starting gas next travels to the inlet of the pneumatic starter motor, where the pressurized gas causes the starter to rotate. The starter shaft, in turn, drives the splined interconnect shaft of the engine. Once the gas has gone through the starter motor, it will exhaust out to vent with no more than 5 pounds back pressure. Also in the start system, there is a buffer oil valve which is pilot operated and is used to isolate the lube oil in the bearing and the starter clutch assembly from the starter gas and the starter housing. The final start system topic we need to review is the timing or sequence of all the starting functions we've been discussing. We'll be using this block diagram. This particular diagram contains only start system related events. However, we'll be using similar block diagrams to explain other subsystems. Before going on to the start system diagram, let's briefly review the symbols and terminology associated with this type of diagram. In all cases, the block diagrams are meant to be read from left to right. As we read across, we see events occur at a certain time, for instance, 15 seconds, or at a certain speed, such as 13%. In this manner, we will come upon the event symbol in the exact order that the actual event occurs on the package. When symbols are stacked in a column, this means the events happen at the same time. As you can see, a major event is represented by a yellow block, while a timer is represented by a blue circle. The dotted line represents its timing interval. The bold black line represents the intended path of events when everything is working correctly. A yellow block with a broad border signifies a critical speed set point. When any yellow block has an arrow, such as this example, this means that a decision must be made whether the requirement in the block was met or not. In this example, if a minimum speed was not achieved by the time the timer times out, a package shutdown will result. Now, let's apply this to the actual start system block diagram. At the moment the start switch is pushed, a 10-second timer is energized to allow for a pre-lube period. When the timer times out, three events will occur. A 90-second start timer will energize, the 15-second crank timer will energize, and the control system will signal the starter to begin cranking the engine. As the engine begins to accelerate, 13% engine speed must be achieved before the 15-second crank timer times out, or there will be a fail to crank shutdown. As long as 13% was successfully achieved within 15 seconds, the next major start system event will be at 60% speed, where the start system will be turned off. The engine must now accelerate to 90% speed under its own power before the 90-second start timer times out, or the package will shut down on fail to start. If 90% speed was achieved by 90 seconds, the engine's acceleration to 100% speed will continue. This concludes the start system lesson. You may wish to review your student workbook or proceed on to the next lesson. In this lesson, we'll discuss the operational characteristics of the electrical start system. Some of Solar's Saturn-driven generator sets are started by an electrical start system similar to the one shown here. In the past, however, Solar has manufactured three different electrical start system configurations. The earliest start system consisted of a disengaging jaw-type starter motor with an exterior-mounted solenoid that mechanically shuttled the motor's armature forward to engage the clutch. The next start system evolution still used the disengaging jaw-type clutch, but now the armature magnetically shuttled to engage the clutch. The latest version Solar is currently installing on Saturn generator packages no longer uses the shuttling disengaging clutch. The new configuration uses a fixed rotating armature that connects to the accessory drive through an overrunning Sprag clutch assembly. Because there are so few of the newest configurations in the field, and the earliest model is relatively outdated, this video lesson will concentrate on the second configuration, which uses the disengaging jaw-type clutch that is magnetically shuttled to engage the starter motor. The overall purpose of this electrical start system is to provide the initial rotation to assist the turbine engine to get to 60% speed. The components that assist in providing this starting rotation include the 24-volt DC starter motor, a contactor box containing a start contactor and a small electronic control board, the accessory drive jaw clutch, a connecting wiring harness, and a set of control relays located inside the control console. The starter motor itself is a series-wound 800-amp 24-volt DC motor. As mentioned earlier, the motor assembly has a retractable jaw clutch that must extend to engage the accessory drive adapter jaw. This engaging process is accomplished by generating a magnetic field inside the motor housing that slowly shuttles the motor's armature to engage the clutch assembly. This magnetic field is controlled by the start contactor located on the starter motor housing. Because the shaft's lateral movement takes 1 to 2 seconds before the starter motor begins to rotate, the contactor is sometimes referred to as the soft start contactor. As a result of the motor's armature extending, the starter motor jaw mates with the accessory drive jaw to transfer the motor's rotational torque to the turbine engine. The wiring harness electrically connects the starter assembly to the control relays located inside the control console. Let's now take a moment to discuss how these components work together to assist the turbine engine to reach 60% speed. The starter motor assembly receives its energizing command signal from the start relays located inside the control console. This command signal first energizes the soft start contactor, which shuttles the motor's armature to engage the jaw clutch assembly. 1 to 2 seconds after the jaw clutch engages, the main contactor energizes and causes the starter to begin cranking the engine. Assuming combustion has occurred, the starter will now aid the turbine engine's acceleration to 60% speed. Upon reaching 60% speed, the soft start and main contactors are de-energized, which causes the jaw to retract and the motor to coast to a stop. The engine will now accelerate on its own power up to rated speed. The final start system topic we need to review is the timing or sequence of all the starting functions we've been discussing. We'll be using this block diagram. This particular diagram contains only start system related events. However, we'll be using similar block diagrams to explain other subsystems. Before going on to the start system diagram, let's briefly review the symbols and terminology associated with this type of diagram. In all cases, the block diagrams are meant to be read from left to right. As we read across, we see events occur at a certain time, for instance, 15 seconds, or at a certain speed, such as 13%. In this manner, we will come upon the event symbol in the exact order that the actual event occurs on the package. When symbols are stacked in a column, this means the events happen at the same time. As you can see, a major event is represented by a yellow block, while a timer is represented by a blue circle. The dotted line represents its timing interval. The bold black line represents the intended path of events when everything is working correctly. A yellow block with a broad border signifies a critical speed set point. When any yellow block has an arrow, such as this example, this means that a decision must be made whether the requirement in the block was met or not. In this example, if a minimum speed was not achieved by the time the timer times out, a package shutdown will result. Now, let's apply this to the actual start system block diagram. At the moment the start switch is pushed, a 10-second timer is energized to allow for a prelude period. When the timer times out, 3 events will occur. A 90-second start timer will energize, the 15-second crank timer will energize, and the control system will signal the starter to begin cranking the engine. As the engine begins to accelerate, 13% engine speed must be achieved before the 15-second crank timer times out, or there will be a fail to crank shutdown. As long as 13% was successfully achieved within 15 seconds, the next major start system event will be at 60% speed, where the start system will be turned off. The engine must now accelerate to 90% speed under its own power before the 90-second start timer times out, or the package will shut down on fail to start. If 90% speed was achieved by 90 seconds, the engine's acceleration to 100% speed will continue. This concludes the start system lesson. You may wish to review your student workbook or proceed on to the next lesson.
The fuel system, in conjunction with the electrical control system, automatically controls the flow and pressure of fuel to the engine. Proper fuel scheduling is necessary to ensure a smooth ignition during start, to prevent the engine from going into surge at low speeds, and to make sure that full power will be delivered under any load condition. This illustration shows the flow path of the main fuel supply. Gas fuel enters the fuel system and is filtered at the inlet strainer. Next, it flows through the primary and secondary fuel shut-off valves and goes to the fuel control valve. Regulated gas fuel then flows to the torch igniter and to the manifold through these three fuel line connections that feed fuel into the combustor through 9 fuel nozzles. The main topics for discussion in this lesson will include a description of the system components, including their function, location and operation, a system functional description, and a block logic description of the fuel system events during a package start. Prior to entering the gas fuel system, fuel flows through a manual fuel shut-off valve. This customer furnace ball-type valve is manually opened prior to engine startup. In situations where no fuel pressure can be present, such as during maintenance or when the package is to be shut down for an extended period of time, the manual fuel shut-off valve must be closed. The advantage of a ball-type valve over other designs is that in the event of an emergency, the ball-type valve can be quickly closed with a quarter turn of the handle. Initial filtering of gas fuel takes place at the Y-shaped cast steel strainer with a 40-mesh cylindrical screen. A clean-out plug located on the lower branch can be removed for cleaning. An optional gas fuel filter may be installed off-skid. If a duplex filter system is selected over a simplex system, one filter can be shut off and cleaned while the package is in operation. This is accomplished with ball valves installed in the inlet and outlet plumbing lines to its filter, providing for individual fuel shut-off. The primary fuel shut-off valve is located downstream from the fuel inlet strainer on the fuel manifold. The valve has 3 major components built into it: a pilot gas filter, a normally closed pilot solenoid valve, and the main normally closed spool-type valve. Here's how it works. First, in the de-energized, normally closed position, gas fuel supply enters the inlet port, goes through a pilot filter, and stops at the normally closed pilot solenoid valve. At approximately 13% engine speed, the solenoid valve energizes and opens, venting gas at the closing side of the solenoid. Pilot pressure is now admitted to the open side of the spool valve, shuttling it to the closed position. This causes gas at the closing side of the spool valve to vent. With the primary fuel valve fully open, supply gas can now flow through the open port of the valve to the secondary fuel shut-off valve. The secondary fuel valve is a 2-way, spring-loaded, diaphragm-operated, normally open valve. It is located on the fuel manifold downstream from the primary fuel valve. The secondary valve acts as a backup to the primary valve in case the primary valve fails to close due to contaminants or other factors. The pilot solenoid valve, also called the vent valve, is located at the engine junction box. The normally closed 3-way valve is connected to the pilot control side of the secondary valve, to the upstream side of the primary fuel valve, and to the vent line. The secondary fuel valve and the pilot solenoid valve operate together like this. At approximately 13% engine speed, the solenoid valve energizes and closes the vent port. The pressure port opens and applies pressure to the control side of the valve diaphragm. Spring pressure combined with pilot pressure holds the valve open during operation. Should the primary valve fail to close when the engine is shut down, the fail-safe function of the secondary valve goes into effect and the valve closes. Remember that when the stop switch is pressed, the DC signal to the pilot solenoid will be interrupted. The pressure side will close and the vent will open. So, the loss of pilot pressure to the control side of the valve diaphragm means that supply side pressure will overcome diaphragm spring pressure and the valve will close. In fact, the secondary valve will close when supply side gas pressure increases by 1 to 3 psig. Incoming gas fuel pressure is monitored at the gas fuel pressure switch. The switch located at the package junction box will prevent package startup or cause a shutdown if fuel pressure is outside of the preset limits. A pressure gauge continuously displays the pressure level in the fuel supply line. The gauge is mounted on the engine gauge panel at the forward end of the package. Gas turbine engines require an exact proportioning of fuel and air to achieve a smooth acceleration and to ensure that the engine doesn't go into surge during start. The fuel control valve, located downstream of the secondary fuel valve, functions to provide this critical fuel-air balance. The valve consists of a 100-micron pilot filter that prevents impurities from passing through the pilot gas orifice, a spring-loaded diaphragm-operated main poppet valve that, when opened by controlled gas pressure, allows gas fuel to pass through the throttle valve, two spring-loaded diaphragm-operated flopper or loader valves that close as a result of PCD and spring tension and open by controlled gas pressure, and a butterfly-type throttle valve that is operated by a linkage system from the governor actuator. The throttle valve has a flat blade within the fuel passageway that adjusts its angle to regulate the size of the flow path. The most important point to learn about the fuel control valve is how and why the loader flopper valves operate so that the engine will accelerate smoothly. This graph shows a fairly rapid acceleration of the turbine up to approximately 45% speed, then a somewhat slower rate up to rated speed. Up to this point in the fuel schedule, the number one loader is in control. You can see that if this rate of acceleration were to continue, the engine would go into surge. So, to avoid surge, the number one loader closes, slowing the rate of acceleration, and the number two loader controls the flow of fuel through the remainder of the acceleration schedule. The loader valves do not close at the same time because their adjusted spring tensions and diaphragm sizes are different. A precise calibration of the loader springs is critical to achieving a smooth start. The position of the flopper valves at any given point in the acceleration schedule is a direct result of the relative values of PCD and spring tension on the closing side and control gas pressure on the opening side of the flopper valve diaphragms. The position of the flopper valves determines what will be the control gas pressure on the opening side of the poppet, and finally, how much fuel will flow into the system. At 100% speed, the poppet valve moves to its null position. This action continues as a modulation function as the speed governor calls for control action and maintains engine speed. The igniter torch assembly is made up of a housing which incorporates a gas fuel line connection port, a filter and orifice, and a spark plug electrode. Ignition takes place when a small amount of gas fuel flows through the igniter plug housing and is ignited by spark from the spark plug. This creates a torch that ignites the fuel-air mixture in the combustion chamber. The fuel manifold and nozzle assembly is the last component that gas passes through prior to entering the combustor. You may have noticed that this engine is constructed somewhat differently than the one you saw in the first module. Both engines use gas fuel, but this engine has the standard gas fuel manifold, whereas the other engine was equipped with a dual fuel manifold. The assembly consists of a two-piece manifold and 9 fuel nozzles. Fuel enters the fuel manifold through 3 fuel line connections and is distributed to 9 nozzles that protrude through grommets into the combustor dome. The final component in the system is a drain check valve. Liquids that accumulate as byproducts of combustion or residue of fuel gas are drained from the turbine through 2 drain check valves. The normally open reed and half ball valves remain open when the engine is shut down so that liquids can drain. During startup, PCD eliminates any residue that may be present in the combustor by blowing it out of the drain valves. During engine operation, combustor pressure of 3 to 5 psi closes the valves to prevent bleed action. With the aid of this gas fuel schematic, we will follow the path that fuel takes to the combustor when the engine is started. First, the customer furnished manual fuel shutoff valve is opened and gas pressure enters the system, flowing through the inlet strainer and filter and stopping at the closed primary fuel valve. As the engine begins rotating, after initiation of start, the governor actuator receives an electrical signal to move the throttle valve to the full open position. Up until 90% speed, fuel flow is scheduled by the fuel control valve, not the governor. 10 seconds after turbine reaches 13% speed, the primary and secondary pilot solenoid valves energize and pilot gases open the primary fuel valve and maintains the secondary fuel valve in its normally open position. At the same moment that the fuel valves are opened, ignition occurs. 25 seconds after fuel and ignition, the torch igniter is turned off. Acceleration continues as the fuel control valve meters fuel in accordance with PCD. At 90% speed, the governor bias relay is de-energized and the throttle valve is controlled by signals from the electric governor control to the governor actuator. The last part of the gas fuel system lesson is really a review of what you learned in the functional description. The difference being the use of a block diagram to illustrate the sequence of events. First, we'll assume that the manual fuel shutoff valve has been opened by the operator. Next, the start switch S110 is pressed and released. The governor bias relay and the governor actuator energize, causing the throttle valve to fully open. 10 seconds after engine speed reaches 13%, several events take place. The primary and secondary pilot solenoid valves energize, and the fuel valves open. The ignition exciter relay, the ignition exciter, and the igniter plug are energized. The igniter plug ignites the fuel-air mixture, and the engine continues to accelerate. The light-off timer is de-energized and starts to time out. When the light-off timer times out, the ignition exciter relay, the igniter plug, and the ignition exciter will be de-energized. Ignition is off and combustion is self-sustaining. The next fuel system event occurs at 90% speed. At this point, the governor bias relay is de-energized, and the governor actuator controls the opening of the throttle valve via signals from the electric governor control. To increase or decrease the amount of fuel to the combustor, thereby changing engine speed, the operator manually adjusts the speed adjust switch. You will learn more about speed control in the governor lesson. This ends the gas fuel system lesson. Please read the student guide before going on to the next lesson. If you still have questions after reading the manual, you may wish to view the video portion of the lesson again before answering the questions in the guide.